Light has always been our guide to the universe. It reveals the stars, encodes information, and shapes the tools of modern science. But what if we could shape light itself? What if we could twist it into a spiral, launch it through plasma, and pull it into a completely different state of energy and form? One that pushes the limits of what light is even supposed to be. In a new study published in Communications Physics, researchers simulated exactly that. The paper is titled Photon Acceleration of High Intensity Vector Vortex Beams into the Extreme Ultraviolet. They began with a vortex of light, structured, polarized, and full of angular momentum. Then they sent it through a wave of plasma, an ocean of charged particles rippling behind a high-speed electron beam. What emerged was not ordinary light. It was something sharper, shorter, more powerful, compressed in time, shifted in frequency, and still structured. This has not been built in a lab yet, but the simulation used real-world parameters, and what it revealed might be the future of attosecond imaging, next-generation computing, and even quantum optics. Let's break down what happened and why twisting light like this can change everything. When we imagine a beam of light, we tend to picture something simple, a straight, narrow ray, maybe with a color or a flicker. But light can be far more complex. It can carry shape, it can twist, it can have structure. In physics, one of the most fascinating examples of this is the vector vortex beam. This type of light carries optical angular momentum. It does not just move forward, it spirals as it moves, like a corkscrew made of photons. And unlike ordinary laser beams, vortex beams can have a donut profile, with a dark center and a spinning phase around it. But the structure does not stop there. In a vector vortex beam, the polarization of light, meaning the direction its electrical field points, also varies across the beam. This makes the beam even more intricate, with patterns that shift depending on how you look at it. These beams are not just theoretical, they have already been used in tools like optical tweezers, where they can trap and rotate tiny particles. They have been explored in quantum communication, where different twists can encode different bits of information. And they have also opened up new dimensions of microscopy, allowing scientists to see structures that were previously invisible. But until now, all of this was done in relatively low energy environments, the visible or near infrared light, in a controlled lab setting. We'll see why that twist and even the structure it carries matters even more when you push light to the extreme conditions. There's a phenomena in plasma physics called photon acceleration. Despite the name, it's not about making light move faster. Photons already travel at the speed of light. Instead, it is about shifting their frequency and with it their energy. Here's how it works. When light passes through a medium like air, water, or plasma, it experiences something called refractive index, which affects how fast it moves. In a plasma, that refractive index can vary in both space and time, especially when the plasma is disturbed by something powerful. In this case, scientists used a 50 giga-electron-volt electron beam to drive a wake through the plasma. This wake is a moving ripple, an area of lower electron density trailing behind the beam, traveling nearly the speed of light. That ripple creates a dynamic, refractive index, and when a beam of light enters it, the changing conditions act like a ramp, causing light's frequency to rise as it travels through. The researchers launched an 800 nanometer vector vortex beam into this wake. As the light passed through, it went through a dramatic transformation. Its frequency increased, its pulse compressed in time, and most critically, it maintained its structure. To test this in detail, the team ran high-resolution simulations using OSIRIS, a well-known particle in cell code for modeling plasma behavior. They used a boosted frame approach to simulate relativistic speeds with high efficiency and fidelity. The input was a tightly focused optical vortex beam with intensity just under 10 to the 18th watts per square centimeter. As it traveled just 1.2 centimeters through the plasma, its wavelength compressed from 800 nanometers to 36 nanometers, deep into the extreme ultraviolet. Its peak intensity jumped above 10 to the 20 watts per square centimeter, and the duration of the pulse dropped to below a femtosecond, potentially into the attosecond range. But the most striking result, the beam did not fragment. It held its shape, twisting phase, polarization structure, donut-like profile, all intact. This process does not just generate high-energy light. It generates structured high-energy light, something rarely achieved in the extreme ultraviolet. And it fills a gap in our technological toolkit, one that's usually too high for traditional optics and too complex for many large-scale accelerators. This was not just a concept that looked good on paper. The simulation shows that vortex beams can be reshaped, accelerated, and compressed without losing what makes them special. So why would anyone go to such extremes to twist a beam of light, launch it through plasma, and fire it into the extreme ultraviolet? Because the results unlock an entirely new class of light, structured, compressed, and packed with energy at scales we've rarely had control. One of the most exciting applications is attosecond imaging. To watch electrons move in real time, you need pulses that are incredibly short, less than a quadrillionth of a second. Some extreme ultraviolet systems can already produce pulses this fast, but they're often bulky, expensive, and lack the structured coherence of this new approach. This simulation points to a possible way of generating attosecond vortex beams, a tool for exploring the quantum world with both temporal and spatial precision. And then there's the nanofabrication and advanced lithography. The wavelength of light limits how small we can etch or manipulate matter. Extreme ultraviolet already pushes those limits, but a vortex beam in that domain, that could offer new ways to rotate, trap, or direct particles at the nanoscale with precision that standard light simply can't match. There's also the potential in quantum information science. Photons with angular momentum can encode more than just binary on-off states. They can carry a twist, a spin, even a sequence. Structured light opens up the door to more complex information systems, and doing that in the extreme ultraviolet range could one day lead to quantum protocols that operate at vastly smaller scales or faster speeds. Finally, there's the question of scale. This beam did not need a kilometer-long accelerator or a billion-dollar facility. Everything happened inside 1.2 centimeters of plasma. A device like this could one day sit on a tabletop, offering access to energy states we once thought were locked away from us. We've seen plasma generate exotic behaviors, pinching into filaments, self-organizing, even acting like memory. But here, plasma becomes something else entirely, a lens that reshapes light and a bridge that moves it into a new domain. Right now, everything we've discussed exists in simulation, but the gap between simulation and experiment is getting smaller by the year. The core components already exist. Plasma wakefields like the one used here are being studied at research centers. The 50 giga-electron volt electron beam, already in use. Ultra-short high-intensity lasers, also available. Even vortex beams, once niche, are now part of mainstream photonics. What hasn't been done yet is combining those elements to accelerate structured light through a plasma wakefield and measure the result. It won't be easy. The beam has to be precisely aligned with the wake, the pulse must be synchronized with the moving refractive index, and the output must be verified both in frequency and in structure. But if it works, we'll have more than just a new kind of ultraviolet beam. We'll have a new kind of control over the shape, energy, and function of light itself. Science often moves through four phases: idea, simulation, experiment, and application. Right now, we're sitting between phases 2 and 3. And if the real world test matches the simulation, this won't be just a physics curiosity. There's one more layer to all of this, something that doesn't quite fit the technical checklist, but lingers in the background. We have just seen light behave in a way we don't usually expect. It didn't just travel, it didn't just reflect or even refract. It transformed. It was compressed, reshaped, and launched into a new domain while still holding on to a complex internal structure. It's easy to forget that light is supposed to be massless, untouchable, uncontainable. But in this experiment, it behaves more like an object, something with structure, coherence, and memory. What does it mean when light begins to blur the line between wave and matter? What happens when a beam of energy starts acting like a thing? Hopefully, you'll let me know what you think in the comments below. Some researchers have long speculated that light, when shaped correctly, could do more than just illuminate. It could interact with fields, with particles, even with life. Whether that's in the form of photonic crystals, biological coherence, or yet undiscovered modes of information, the possibility remains open. We don't have the answers to those questions here, but they are waiting just on the other side of the ultraviolet. Light is no longer something we shine. It's something we can shape, twist, compress, accelerate, and maybe even one day use to explore the realms we have not yet imagined. This study did not just create a new kind of beam in the lab. It showed us how we could. And when that beam is finally built, it might not just reveal new things. It might be one. Thank you so much for joining me today. I'm Adrienne. Welcome to Biolumination. I can't wait to see you next time.